Welcome back to Online Calculus 2. This is part 2 for our online lectures for improper integrals. In this video, we're going to learn about the comparison test for improper integrals. All right, so we left off in part 1, the previous video, addressing what improper integrals are. And there's two types. There's the ones that deal with infinities in the limits of integration, regions that are infinitely long. And then the second type are those dealing with functions that have vertical asymptotes, where the regions might be infinitely tall. Now, what we have up on the screen here are 3 examples of improper integrals of the first type. Notice there's infinities in all the integral signs. And these span a range coming from topics from integrals from mathematics and physics. So that first one there, the improper integral of e to the negative x squared, this is referred to as the normal distribution coming from statistics. You might know this also called the bell curve. So in your statistics course, if you've taken that, you might have recalled dealing with z-scores. How all those z-scores are calculated comes from that first improper integral. The other 2 improper integrals there come from a combination of other topics in mathematics and physics, and we'll kind of see how to determine some things about them moving forward. Now, the last example there, the integral of x cubed divided by e to the x minus 1, this improper integral, for whatever this topic called black body radiation is, that integral represents something about the total energy emitted. And for that physical process of black body radiation, you might want to know how much energy is emitted. And to do that, you'd have to evaluate that integral. Now, if you take a look at all 3 of those functions you're integrating, all of these are exceptionally difficult, if not impossible, to find antiderivatives for. The first one, e to the negative x squared, that function has no antiderivative. So no matter how hard you try, there's no antiderivative that exists for that function e to the negative x squared. And same goes for the other 2. There may be antiderivatives, but I'll say they're exceptionally difficult to find. As you continue on your mathematical journey, maybe going through what occurs beyond Calc 4, going all the way up to Calc 27, you might learn how to evaluate those in following mathematics and engineering and science courses. All right, so the question we're left with here is, what do we do if these integrals are too hard to evaluate? We still might be interested in determining if the improper integrals converge or diverge, if they give finite or infinite areas. Before we move on, notice next to each integral, I put a number, which is the value for the integral. So what we have here is all 3 integrals equal finite numbers. All 3 improper integrals are convergent. Now, what's interesting about all those numbers is notice they all have pi in them. And that's one thing that myself and other mathematicians and scientists consider interesting, why pi pops up in the values of these integrals. That requires a deeper answer, which you might get to much later in your mathematical journey. Right now, we're just primarily concerned with determining if these integrals converge or diverge. All right, so these are too difficult to evaluate. How can we determine their convergence or divergence? Well, we have a nice tool called the comparison test. And what we start with are 2 functions, g of x and f of x. One is less than the other. Graphically, what that means is g of x, its graph is below the graph of f of x. And since one graph is beneath the other, recall integrals represent area. The function on the bottom should have less area beneath it than the function on top. So we have that inequality for the 2 improper integrals there. The improper integral of g of x is less than that of the improper integral of f of x. All right, now with this comparison there, saying one improper integral is less than the other, there are 2 conclusive possibilities. The first is if the bigger improper integral is finite, then the smaller one has to be finite as well. Intuitively, we think of convergence and divergence as being finite values or infinite values for the improper integrals. Mathematically, we call those terms the improper integrals converge or diverge. So we get this first conclusive possibility. If the improper integral of f of x converges, if that's finite, then the smaller one for g of x has to converge as well. It also has to be finite. Now that's the first conclusive possibility. There is another conclusive possibility, which is if the smaller improper integral is infinite, if the improper integral for g of x diverges, then the bigger one has to be infinite. It has to diverge as well. All right, and those are the only two conclusive possibilities. Be careful, there is a third possibility which is inconclusive with this comparison test. That inconclusive possibility is if the bigger improper integral is infinite or diverges. Then anything can happen for the smaller improper integral. If the bigger is infinite, the smaller thing could be infinite or it could be finite. And that is the inconclusive possibility. So just be careful, there's only two conclusive possibilities that we can apply with the comparison test. Now, before we get to some examples on applying the comparison test, we need some functions and improper integrals that we can do our comparisons with. One of the drawbacks of the comparison test is it requires you, with your given improper integral, to know what you're comparing with. And that's a little bit difficult to come up with. It's like finding the functions you would need in Calc 1 for evaluating a limit with the squeeze theorem. All right, now one useful way to come up with a comparison is by using what we introduced in the last video called the P integral. The P integral is specifically an improper integral from 1 to infinity. The limits on the integral have to be from 1 to infinity, no other values. And the function has to be of the form 1 over x to a power. The nice thing about this is it's very quick and easy to determine if the improper integral converges or diverges based off of the value for that exponent p. If p, the power, is bigger than 1, the improper integral converges. There's the value there for it, 1 over p minus 1. And if p is equal or less than to 1, the improper integral here diverges. All right, this is going to be popping up a lot in the examples where we apply the comparison test. All right, a second way to come up with functions to do the comparison with, think back to those examples from the previous page. All those functions, a lot of them contained fractions. So let's think about how to make fractions bigger or smaller. One way to make a quantity or fraction bigger is to make its denominator smaller. All right, an inverse result to that is we can make a quantity or fraction smaller by making the denominator larger. Now, before we get to the examples, let's take a look at just a simple illustration of how that second part gets used. Let's say we had the quantity or expression or function 1 divided by 1 plus x to the 4th. Now, what we're going to be thinking for examples with the comparison test is we might want to look for something bigger or smaller. That's required with applying the comparison test. And to get an idea if we would look for something bigger or smaller, we would first need to think if our function and improper integral converges or diverges, if we have an idea of that. Now, this is close to the P integral function, 1 over 1 plus x to the 4th, but that plus 1 in the denominator screws that up. Since this is close, it looks kind of like 1 divided by x to the 4th. We might think it looks like a convergent P integral, since the exponent value is 4. Now, since we think this function and its improper integral is likely to converge, from our comparison test for a conclusive result, we will need to find a bigger function that we know for sure converges. All right, so for this fraction, we can find something bigger by making the denominator smaller. One way to make that denominator smaller is to get rid of the +1. That makes your denominator smaller, which then gives you a bigger fraction. 1 divided by x to the 4th is greater than or equal to 1 divided by 1 plus x to the 4th. Notice there, your denominator became smaller, which is why we have that expression or quantity now being greater than. So we're going to be doing similar arguments like that when we apply the comparison test in the following examples. All right, so for our final example, continuing from the examples we did in part 1, we're going to look at example 5 here, which is basically given an improper integral. We're going to try to determine if it converges or diverges. Almost all the examples you're given when you're applying the comparison test usually are exceptionally difficult or impossible to evaluate exactly. In other words, to get the exact value for these improper integrals. Here, we're going to be able to quickly answer that just by applying the comparison test to determine if they converge or diverge. All right, the first part, part A, is a little tricky. So to get an idea if it converges or diverges to guide us for looking for a bigger or smaller function, let's take a look at how we might think of that. All right, so for the function 1 divided by 1 plus x to the 4th, if x is a very large value, that +1 in the denominator is insignificant compared to x to the 4th when x is large. So for large values of x, 1 divided by 1 plus x to the 4th, it's pretty darn close to 1 divided by just x to the 4th. Now, since that approximation looks like the p integral function, 1 over x to the 4th, we think here the exponent is 4, bigger than 1. So this looks like a convergent p integral function. We think our improper integral here for part A looks like it might converge. From our comparison test, if we think our integral converges, we have to look for a bigger function, an improper integral, that we know for sure converges. All right, from our tips, we can use the comparison here, 1 divided by 1 plus x to the 4th. We can say that is less than or equal to 1 over x to the 4th. Now be careful here. Notice the limits in the problem on the integral sign are from 0 to infinity. Now, while that approximation is correct, the resulting improper integral from 0 to infinity of 1 over x to the 4th, that actually diverges. Notice this falls into the second type of improper integral. There is a problem with that lower limit on the integral, x equals 0. If you were to plug that in, you get division by 0. This improper integral is of type 2. There's an infinite discontinuity, a vertical asymptote in that region of integration from 0 to infinity. Now, notice we have there 0, the lower limit, which is not 1. So this is not a p integral. So the comparison here kind of breaks down with the limits on the integral from 0 to infinity. All right, so what do? The comparison is correct with 1 divided by 1 plus x to the 4th being less than or equal to 1 divided by x to the 4th. But how do we deal with the limits from 0 to infinity? We're going to recall kind of a property of integrals where we can split the improper integral from 0 to infinity apart to two separate integrals. We're going to split it apart from 0 to 1, and then another improper integral from 1 to infinity. Now, what this gains us is the ability to split this into two parts. That first improper integral from 0 to 1, it evaluates to some number. Notice that first integral from 0 to 1 of 1 divided by 1 plus x to the 4th. It is not improper. There's no problems with the limits 0 to 1. There's no division by 0, no vertical asymptotes. So that first integral is a familiar proper integral and it evaluates to some finite number. The second improper integral from 1 to infinity, that is now one with the lower limit being 1 that we can compare with our p integral. Compare with the function, an improper integral from 1 divided by x to the 4th. Now that is a convergent p integral. It's a p integral because the lower limit is the value 1, and since the exponent, the p value, is 4, bigger than 1, this is a convergent p integral. And by comparison, that improper integral from 1 to infinity is convergent as well. All right, so we have, for those two integrals, the second integral is convergent. That means that improper integral is finite. The first integral there from 0 to 1 is also a finite number. If you add two finite numbers together, you get another finite number. And what that concludes for us, or what we can conclude from that, is that the original one from 0 to infinity is convergent. All right, this one was, as it turns out, a little bit tricky because the limits on the integral were 0 to infinity. The second one, in part B, is a little more straightforward. Now you have a sense maybe for how the comparison test works, how we incorporate finding comparison functions and using the p integrals for this. Maybe pause the video and give yourself an attempt at part B. We'll check back in a few minutes and go through the problem after that. All right, welcome back. Hopefully you are enjoying the lovely incoming ocean waves we have there. All right, as we go through this one, we're going to kind of start off trying to get an idea if we think our improper integral converges or diverges. If we think our given integral converges, we would look for a bigger function to apply the comparison test. If we think our improper integral diverges, we would look for something smaller that we know diverges. All right, we're going to do our large X approximation here. When X becomes a very large value, that +1 in the denominator doesn't make any difference. Think of X as being very large. A very large number raised to the 6th power is huge. Adding 1 to that doesn't really change it at all. So for large values of X, this function behaves like X, the numerator, divided by X to the 6th, which reduces and simplifies to just 1 over X to the 5th. Now, if you think back to the p integral, 1 divided by X to the 5th, that exponent 5 puts this into the convergent p integral case, since the p value here, the power of X, is greater than 1. So what we think for this problem is because it looks like a convergent p integral function, our improper integral, we might think, converges because they look similar. And since we think our improper integral converges, we would look for a bigger function for comparison. All right, so we're going to use our same trick that we addressed kind of earlier in this video. We can make our denominator smaller by getting rid of the +1. When you make your denominator smaller, that gives you a bigger quantity or fraction. So we get our comparison here. Our function, x divided by 1 plus x to the 6th, is certainly less than or equal to 1 over x to the 5th. All right, the rest of the problem is pretty straightforward. There's no problems with the limits. 1 to infinity are the correct limits for the p integral. So we have this comparison here. Our improper integral is less than the improper integral from 1 to infinity of 1 over x to the 5th, which is a convergent p integral. So what we can conclude from the comparison test is that the bigger improper integral converges, which means the smaller improper integral has to converge as well. And that's basically it. So we conclude for our improper integral, it is convergent. What we can't figure out is what is the exact value that that improper integral equals. All right, hope you enjoyed the video. Stay tuned for following lectures in our online series for Calc 2.